Hi students. So today we are going to start optimization tutorial 19, and today what I'm going to do is to review the different gradient based methods. So essentially we are going to look at steepest descent and the 6 conjugate gradient methods we have discussed, and we are going to use some simple examples and Python code to actually delve deeper into these methods and also look at plotting some of the results. So that's going to give us a good idea about the methods as well as teach us certain new things about Python programming. I'm Dr. Ganguly. So in today's video, we are going to look at the gradient based methods, the steepest descent, 6 conjugate gradient methods, and we are going to explore as to what happens to the angles between the search directions, that is dk and dk plus 1. We are also going to look at the trajectory of convergence, that is the path of the design vector as you go from the starting point to the final optimal point. And we are going to do all this thing using Python code. Now you should also take a look at optimization lecture 19, which is the corresponding lecture in this particular tutorial or corresponding to this tutorial. And then you will be able to figure out some more aspects about this particular set of methods. Now remember, as far as direct search methods are concerned, they move in the design space using the formula xk plus 1 equals xk plus alpha k dk, where dk is the search direction, alpha k is the one-dimensional step size, xk is the current design vector, and xk plus 1 is the next design vector. So of course the simplest gradient based method is the steepest descent method, and in this method what happens is that we say that the search direction dk is negative of ck or negative of the gradient vector. Now of course you will need a starting point to start off any of these methods, so x0 is presumed to be given, and then following this particular value of x0 you can calculate immediately using this direction that x1 is going to be x0 plus alpha 0 d0 and so on. So that's the simplest method which we use as a kind of benchmark method to compare all the other gradient based methods with. Now what happens in the conjugate gradient method is that you add a particular component to this dk search direction, which is that dk is now minus ck, which was the steepest descent search direction, and you add this plus beta k dk minus 1 term. So this term essentially creates the conjugate gradient method, and there are different methods depending on the different expressions for beta k which have been obtained by different researchers over the past many decades. So of course, again, in the case of conjugate gradient methods, when k is 0, you do not have access to the k minus 1th point. So what you do is you set d0 is minus c0, which is the steepest descent direction. And of course, x0 has to be given for these gradient based methods to work. And you move in the design space using this formula here, xk plus 1 equals xk plus alpha k dk. And remember throughout that the conjugate gradient search direction is given by dk equals negative ck plus beta k dk minus 1. So this should be in your memory banks out there. Let's start looking at the classical conjugate gradient methods, and these are the methods propounded by Fletcher Reeves, Pollack, Ribier Poliak, and Heston Stiefel. So these methods are given by these formulas out here. The Fletcher-Reeves is probably the simplest formula. So here we simply have the norm of ck divided by the norm of ck minus 1, the whole thing squared. And what happens with the Pollack-Ribier formula is that you have a slightly more complex formula, that is ck minus 1 transpose into ck and ck minus 1 transpose into ck minus 1. So of course you are seeing here that these are basically dot products in the numerator and in the denominator. So what happens is that you get scalar values in the numerator and denominator, and when you divide them you simply get another scalar. So beta k is always going to be a scalar value, and so that's simply a multiplying factor on this dk minus 1 here. Now at some time some of these methods may give you a negative value of beta k, so it is generally suggested that in that particular situation we use the value 0 instead. So what we are doing is that we are reverting back to the steepest descent method at that particular k value. So of course you can see that the Fletcher-Reeves is going to be positive at all time because it's simply the square, but some of these methods, the remaining methods, will give you negative values every now and then. Now there are some newer methods which have come up in the conjugate gradient field, and these are due to Liu Story, Dai Yuan, and also Wei Yao Liu. So we have discussed these in a tutorial before. These formulas are given here, so you can check them out. As of course, in most cases you will see that the complexity of the methods has been going up with the passage of time. So Fletcher-Reeves is probably the simplest method. Some of the methods like Liu Story are not very much more complicated than the previous method, but certainly some of the newer methods being proposed beyond 2000 are quite complicated. For example, the Wei Yao Liu method. Now there are more methods I found in various papers out there, but I don't include them because they have started bringing in more factors into the method. So some factor like mu, some tunable factor, which is essentially used to control beta k. So I am keeping with the methods which are relatively simple in the sense that you simply need the gradient vector at the current point and the previous point, or the search direction at the previous point, to essentially calculate beta k. Now with that review of the different methods out there, let us come to question 1. And here you are asked to write a Python program for the 6 conjugate gradient methods and also for gradient descent. And you need to of course use some 1D numerical search here. And the question is as to what are the angles between dk and dk minus 1 for these methods. The function is given here and we have to start at this particular point 5 minus 5. Now we have used this function many times before in this particular course, especially in the tutorials. So the first thing we do is that we write the Python function to calculate the math function here. And similarly, we have a function which calculates the gradient vector, or which returns the gradient vector. So of course, you know, the gradient is simply obtained by taking the partial derivatives of this function f of x. Now beside this, we have one more function here which is required by the 1D search, which gives us the function value f for a given point xk plus alpha k dk. So these functions are going to be called many times in the main program and in the different programs for steepest descent and conjugate gradient. So let's take a look at the main program. So in this program, we are of course going to start from the point x0 is 5 minus 5. So I have put that here, and I need to import numpy and math. Now I give some values here, the tolerance numbers, the small numbers here, to essentially monitor the convergence of the gradient of the function as well as the one-dimensional search. And I give a max value of 1000 for the for loops. Now what I do is that I have two functions out here. I have a function called steepest and I have a second function called conjugate. And in the steepest function, I sent in x0, that is the starting value. I send the two tolerances and I send this max value. And then this steepest function is going to print out whatever I need inside the function. Now as far as the conjugate functions are concerned, they are all the same function, except I sent in the method here as a character. So essentially I send in Fletcher-Reeves, I send in the different methods out here. And so what the code is going to do, the function, it's going to look at the different method and then it's going to create the appropriate search direction corresponding to the method. That is, the d vector is going to be selected based on the particular method which has been specified. So if you are doing Fletcher-Reeves, you pick that particular d direction. If you are doing Pollack-Ribier, you pick that particular direction, and so on. Now in the conjugate function, what I have done compared to some of the tutorials you have looked at previously, where we were using different functions for the different method, is I put in this method here as a variable which comes into the function. And here what I do is I get the search direction corresponding to the particular method. So I create a new function called d method here, where I send in the method. For example, if it's Fletcher-Reeves, I send in fr. I send in C, I send in C old and D old. So C is of course the gradient vector, C old is the Ck minus 1th value, and D old is the Dk minus 1th value. And what happens in this function is that there is a for loop, and the first thing I do is I set C is the gradient vector, And then for I is 0, I use the steepest descent search direction. Beyond this, I use D is D method, which is the conjugate gradient method I have selected for this problem. I have one more call to this particular function here, equal, which is going to do the one-dimensional search. And in case I is greater than 0, I print out the theta value, which is actually the angle in degrees between D and D old, that is between dk and dk minus 1, and I print it to 2 decimal places. And here I am updating the x vector again using the formula xk plus 1 is xk plus alpha k dk. And finally I save the current D and C, which is the search direction and the gradient, in D old and C old. So these are essentially required for the next round because I need access to dk minus 1 and ck minus 1 for most of these methods. Now finally I have this break statement out here where I check whether the norm of the gradient vector has become lower than tolerance. Remember, tolerance was the small number 0.401, and in that case I print out x. So I basically print out the design vector at convergence, and I print out this theta between dk and dk minus 1 at all values of I greater than 0. Now as far as this particular value of theta is concerned, we can obtain it from the usual definition of the scalar product or the dot product. So the dot product of two vectors is defined as u dot v equals norm u norm v into cos theta. So I can write cos theta in this form here. So if I had two vectors dk and dk minus 1, I call them d and d old, then what I can do to calculate this particular value here is I can take the numerator term, so that's the dot product of d and d old. I take the denominator term, which is the multiplication of the norm of d and the norm of d old, and then I divide it. So I get cos theta is the numerator divided by the denominator. Now at this point, this particular value is simply cos theta, so I need access to the arc cos function in math library, and then this answer is going to be in radians. So to convert it to degrees, I need access to the math.degrees function. So remember that I need to, of course, always import numpy, and here I also need to import math because some of these functions are being used as far as Python is concerned. Now for each of these methods, I define these small and simple functions. So each function essentially takes C, C old and D old, and it gives me this beta value, which is obtained from the formulas we have discussed previously. And then it returns negative C plus beta into D old, which is nothing but this formula in pink, which is common to all the conjugate gradient methods. So as far as Fletcher-Reeves is concerned, this is the simplest expression. In the remaining different functions out there, for example, for Heston, Stifel, for Pollack-Ribier, I also put in a small piece of code which ensures that if beta becomes negative, then I put beta equal to 0. So each of these cases you are going to see this particular value for beta k is put out here. So the advantage is that Python has a built-in function which gives us the dot product. So all we have to do is take the dot product, for example here ck minus ck minus 1 into c. So that's taken here and so on. So these three are coming from the three different expressions here. Now for the newer methods, we have again the expressions. Some of them are relatively simple. So again, you can see all these can be expressed in terms of dot products between the current values of the gradient vector, the previous values of the gradient vector, and also the previous value of the search direction. The previous value of the search direction is also required here in D old. So that's coming from this tk minus 1 part here. So these are for the different methods here, the ls method, the Lewis story, and the Dai-Yuan method. So you can see these here. Finally, the somewhat more complicated method, which is given here, the WYL method, that's given here. It looks complicated, but if you look closely, you will see this is simply a factor. So I define this factor as essentially the ratio of this norm, the norm of ck and ck minus 1. And once I have done that, I can simply write this second expression beta, where I say that you have the dot product of c and c minus this factor into c old divided by the dot product of c old and c old. So all this beta k can be calculated, and this actually cleans up the program. So instead of having a plethora of programs out there, we can now have one program for conjugate gradient, and each of the search direction is calculated from these particular d slash method name functions. Now we do need one more function here which essentially takes in the method and brings in c old and d old, and based on the method it actually calls the function and then it returns the particular value. So that's what is being done here in this if statement. So again you can see if method is Fletcher Reeves, then the search direction for Fletcher Reeves is returned. If it is the next method, then that is returned, and so on. And in case none of these are there, something else is there, basically we say that there is an invalid method. So that's a safeguard in this code. So now as far as steepest descent is concerned, it is slightly simpler. Here I don't need to bother about the d direction so much. So I simply said d is minus c. I call the 1D search, and again I'm printing out the theta value, that is theta between d and d old or dk and dk minus 1. And again I'm checking for the norm here. If the problem has converged, I'm printing out the current design vector. Now, of course, we require the 1D search. So the 1D search is the simplest one here. So essentially what we do is that we move forward in terms like this. So we start with delta, 2 delta, so on. And we basically try to bracket the minimum between q minus 1 delta, q delta, and q plus 1 delta, which you can see is done here. So we go from q in range max and we essentially do this thing here. So that's what's taking place here. And so then we are going to see what can be done next, and we finally calculate a star. We calculate the value of I using these two formulas, and then each time I divide delta by 10. So that's going to essentially help me return a decent value of this particular a value or the optimal point of A. So again, optimization tutorial 7 gives you more detail on this equal interval search out there. Now let us print out some of these values. So you can see I have printed some of these values out, and you can see as far as steepest descent method is concerned, it starts from 5 minus 5 and it takes a relatively long time to converge, but it does converge at the minimum point or very close to the actual minimum point. Now in optimization tutorial 3, I obtained this minimum point using the optimality criteria, that is by setting the gradient vector to 0. Take a look at that. And of course, as you would expect, this angle should be 90 degrees. So of course, numerically, it is somewhat close to 90 degrees because we are dealing with computers here. So now we look at the theta values between dk and dk minus 1 for the three conjugate gradient methods, the classical methods. And these are Fletcher-Reeves, the Heston-Stiefel, and the Pollack-Rebier method. And of course, see, the convergence here is very fast, but the more important thing to realize is that the angle which you are seeing is less than 90 here. So essentially this is something which is very interesting. And for these two methods, you can see in one case theta becomes 90, which means that it is reverting back to the steepest descent method for that particular problem. So in that particular case, for I is 2, what's happening is that beta is becoming negative, and so beta is being set to 0. So that's something which is very interesting. All these methods converge very rapidly, of course, but they have different directions as far as the d vectors are concerned, that you can see from the theta values here. Of course, some of the methods have very similar values, and we are going to see that on the next slide also, where we look at the newer conjugate gradient methods. Of course, as you can expect, all these methods converge to the actual optimal point given here. Now, if we look at the different methods such as Dai Yuan and Wai Yao Liu and Liu story, again, we see these results here. So of course, some of these methods tend to perform well, some of them take a little bit more time, but all the conjugate gradient methods perform much better than the steepest descent method. Now in some of these cases, you can see the method actually gives you a theta of 90 degrees, and that happens because the method here is reverting to the steepest descent method, that is d is becoming minus c because the beta value has come negative. So that part of the code is getting picked up here. In each case, of course, we are coming to the optimal solution. Let us now try to improve our knowledge of Python and just look at the trajectory of the design variables for the same problem. So what we want to do here is modify the Python program for conjugate gradient and steepest descent and plot the trajectory of the design variables from the starting point to convergence. Again, the same function is being used here, and this is the starting design 5 minus 5. So the same main program is used here, and basically I'm going to make some changes in that in the functions also. I'm going to bring in matplotlib.pyplot as PLT that is required for the plotting. And of course, I am going to then call all these different functions out here. So I call steepest descent, that is the function steepest. And then I call the conjugate function many times, and each time I pass the different variables here. So that's what I have been doing here. Now one of the things is I have also modified the steepest descent function to pass SD there. Now let us look at the conjugate gradient function. So here we can see the main difference I have done is that I have included this X list here, which is a list which keeps tracks of the X vector or the design vector. So I start with X0, and then what I do is that each time I get some particular value of this X, I bring it up into the list here. So this particular command is there, the append command, which keeps bringing in any new design vector into X list. And finally, when I converge, that is the gradient vector norm becomes less than tolerance, I print out X, and I also print out this particular plot function. So I call this plot function here, and this plot function is going to take in the X list value, the method, whatever method I am sending it, and it's going to plot that particular trajectory of the X vectors from the starting design to the current converged design. Now in steepest descent, I do a few minor changes also. I put in this method here, and also I keep track of this list. So I have the X list here as X0, and then I continue to build up this list here using the append method. And then finally I plot this particular list here, and again I put in the method here. This method is only going to be used for nomenclature, as you will see soon. So that's the plot function. So in the plot function, what is done is that the list is sent here. So I'm sending the list as points and the method name. And then I'm going to take this list and I'm going to zip out of it the X and Y coordinates. And after that, I'm going to simply plot this XY in a graph here, and the graph size is mentioned here as 4 into 3. You can experiment with that size. Now of course color is blue is mentioned here, and I put label is method here. So whatever method is being fed in, for example fr, st, so on, is going to be put in the label here. So I will know which plot corresponds to which method. Finally I label this X and Y, and I give the title of the plot as plotting a sequence of 2D points. Let us look at the different points here. So for example, the steepest descent starts from this point, 5 minus 5. All of them start from the same point, and then you can see it converges like that. Now steepest descent has a problem that it spends a huge amount of time near the minimum point. So this is because of the zigzag nature of the method. But we will see in the conjugate gradient methods, the Fletcher, Reeves, and the different methods out there. Pollack, Rebier here, and the Stiefel method, Heston-Stiefel method here, all these look very similar. Now they look very similar because we are dealing with very small numbers near this particular optimal point. So that's why the look is very similar. So what the conjugate gradient does is that it selects the second and third search direction very appropriately so that it quickly zooms into the minimum point, whereas the steepest descent keeps going around the minimum point for a long time, and it keeps kind of circulating around that point and takes time to converge. Now if we look at the newer methods and we compare it to the Fletcher-Reeves method, we see the trajectory is very similar. Again, we are dealing with very small numbers here. So the graphs are simply meant to show you the difference between steepest descent and the conjugate gradients. The only thing we can say here is that the steepest descent is not doing as well as the conjugate gradients. Now of course, if you need to look at the actual performance of these different methods, for example the conjugate gradient method, you have to print out the numerical results and see. And you will find in most papers, most publications out there, people will print out the converge results to 10 decimal places or 16 decimal places to compare them very correctly. And so a lot of number crunching is involved in solution of those different type of methods. So now let me leave you with a homework project, or if you are a teacher or professor looking at this particular problem, you can use this for a project in your class. So what we did was the simple problem where we were using x1 and x2 as design variable, but this function could be extended to n-dimensional space, which I have done here. And as you know, the difficult problems are for the student, so you can give this problem as a project. Now, I have solved this problem using optimality criteria before in a purely mathematical sense, but of course, writing this as a Python program would involve some more skills and it would involve some more knowledge in Python. So again, this would probably constitute a good programming projects for a student as part of the class if they are doing an optimization class, or if they are doing a scientific programming class, or if they are studying Python for scientific programming. So today's lecture, I think the final lecture in our gradient based method part of the course, we looked at the steepest descent method and the different conjugate gradient method. Now conjugate gradient method continue to become more and more advanced. There are people publishing paper on these methods. If you search out in Google Scholar, you will find more and more papers are coming out in this field. Now, the important thing in the conjugate gradient is to simply understand this concept that this deflection beta k into dk minus 1, which is done here, this actually gives you a lot of dividends in terms of the improvement in the convergence quality for the problem. And so that's the main concept behind this particular method. Like I've mentioned before, conjugate gradient methods are very powerful low storage methods because they only deal with vectors, and therefore if you are dealing with problems with large size, for example 1000 design variables, 10,000 design variables, then conjugate gradient methods would be the way to go. So I would simply say that today we looked at the methods involving C, or the gradient vector. So as far as optimization is concerned, gradient is king. You will generally have methods which require gradients as far as all different methods are concerned. But in the next series of tutorials out there, we are going to start looking at the Newton type of method where the H matrix will also come into play. So we can certainly see that the H matrix is likely to improve the convergence qualities of some of the methods out there. So in optimization, we can say the gradient is king and the Hessian is queen. So again, that's something you can remember. Again, make it a point to look at optimization lecture 19 for a review of the gradient method and go through all the previous lectures and tutorials which lead to this point where we culminate the problems or the methods which can only be done by using C. So here you see the search direction only requires C, and in the future methods we are going to start using H. So that's going to advance our capability in terms of convergence rate and rate of convergence.